Day 11. Dumbo Octopus. Man, all these... This is all making me want to play Subnautica again. Dumbo Octopus. You enter a large cavern full of rare, bioluminescent Dumbo octopuses. Is that a real thing? Or is it like Dumbo as in Dumbo the elephant? Oh my god, it is. Cool. Dumbo. No one ever talks about Dumbo anymore, the film, compared with other films of that era. They seem to not like the Christmas lights on your submarine, so you turn them off for now. There are 100 octopuses arranged neatly in a 10 by 10 grid. Each octopus slowly gains energy over time and flashes brightly for a moment when its energy is full. Although your lights are off, maybe you could navigate through the cave without disturbing the octopuses if you could predict when the flashes of light will happen. Each octopus has an energy level. So they're single digits. 0 and 9. During a single step, the following occurs. First, the energy level of each octopus increases by 1. We were navigating in the deep ocean via Christmas lights. Well, at this point we are. Before this, we weren't really using any lights, I guess. Oh, no, that you're talking about that sentence there. Seem to not like the Christmas. Yes, because it's a Christmas submarine, so yeah, that's what we had available. It's an elf submarine. We're always the elves. In fact, I think every year we've always played as the elves. Okay, some of these problems don't actually say, but I think you are the elves. Yeah, you're still the elves in that, yeah. This is your last unfinished year. Yep, it is. That's 470 stars. We're almost at 500. So first, the energy level increases by 1. Then, any octopus with an energy level greater than 9 flashes. This increases the energy level of all adjacent octopuses by 1, including octopuses that are diagonally adjacent. If this also causes an octopus to have an energy level greater than 9, it also flashes. This process continues as long as new octopuses keep having the energy level increased beyond 9. An octopus can only flash at most once per step. Okay, that's important, I guess. Interesting. Finally, any octopus that flashed during this step has its energy level set to 0, as it used all of its energy to flash. So this step comes at the very last, so... Ah. Alright, so we don't need to worry about... because we're not actually resetting the energy, so it's not like one octopus flashes and then we have to make sure that it doesn't flash again. You just keep increasing, even if it goes to 10, to 20, to 30 value, whatever. And then at the end, we cap everything back to 0 if it's gone over 9. Alright, that's makes it easier to code then. We don't have to keep a hash set of octopuses that flashed. Fine. Right. Adjacent flashes can cause an octopus to flash on a step, even if it begins that step with very little energy. After step 1, so those all flash. So that flashes the middle one, because he gets hit 1, 2, 3, 4, 5, 6, 7, 8 times. After 100 steps, there have been a total of 1656 flashes. And part 2, I bet, is going to ask for like after 1 million steps or something. So we have to maybe identify cycles. I don't know if this even really has regular cycles. It might be a bit more like a game of life type thing. Anyway. $100 steps. That should be alright. Oh, and it's just that grid. It's not a big grid. That's 10 by 10, so that's 100. Okay, so doesn't look too difficult. So just put this as a list. Actually, int x, cast it to ints, because we're adding 1. Okay, let's just take a look at that. Alright. So basically we need a method that computes a step. Given a grid, compute a step. Alright. So I think the order doesn't matter here. If a bunch of elephants can flash, it doesn't actually matter what order you flash them in. Because any subsequent elephant that's going to be affected by a flash, it doesn't matter if you did A then B, or B then A. It'll still get the same number of flashes, I believe. Elephants. See, now I'm confusing because it was Dumbo. Octopuses. We did have some problems involving like thousands of elephants in previous years as well. So yeah, order doesn't matter. I can't give a concrete reason why order doesn't matter. It just seems intuitive to me that order doesn't matter. There's probably a nice simple mathematical proof of that. Anyway, well, I think the important thing is if order did matter, then they would have specified an order in the problem. But they didn't, so. So I think what we do is program it like the way they've set out. So step 1, the energy level of each octopus increases by 1. The feather totally let him breathe underwater as well. Feather? Is that something from Dumbo? Okay, so step 1. Increase energy levels. All right. It was the thing that made him believe he could fly if he held it. Oh, okay. Yeah, I don't remember much of Dumbo. I remember it had a couple of... Well, it had one controversial scene with the alcohol drinking. Didn't Dumbo get drunk at some point? Or was it someone else? And they were seeing pink elephants and stuff. And there was also quite a traumatizing scene, like the circus scene where Dumbo was being mocked and or being I can't remember exactly what happened, but there was a circus scene which was really horrible to watch as a kid. Dumbo, I think he was being mocked and the audience was laughing at him and stuff. Pinocchio got high on Sig, if that's what you're thinking about. Yeah. That happened. That was... But I do remember something from Dumbo as well. Dumbo does get drunk? Yeah, I think he does. I can't remember why. Was it part of an act? Falls in a barrel or something. Oh yeah. And then he starts seeing pink elephants. Welcome in, Crimino Loden, by the way. Cartoons back in the day, man, they did not hold back. Yeah, there's there's a lot of messed up scenes in a lot of those films. It's 10 by 10, but we'll just... Just go watch Brave Little Toaster. What's that? A non-Disney 90s animated movie, Brave Little Toaster. Haven't heard of it. I remember Watership Down was very messed up, and that should never have been watched by kids. But I'm pretty sure we watched it in school as well. And All Dogs Go to Heaven. That was pretty traumatizing as well. And Hunchback of Notre Dame, another one. So, how are we gonna... Alright, so I think we need to make a... is flashed. That stops us from flashing an elephant. I'm going to be saying elephant from now on. Octopus twice. But we also need like a flashing cue. To flash. This would need to be a set, wouldn't it? Because we don't want to add something to it twice. And then, or it doesn't have to be a set. We can make it a queue and just... So the moment we see that a octopus is ready to flash, we put him in the to flash queue, which will make it easy to pop things off. And we also put him in is flashed, even though he technically hasn't flashed yet, because that just marks him so that he'll never be added to the queue a second time. So if grid ij is greater than 9, flash. Okay, so to flash dot and ij is flashed dot add ij. So that's the first pass. Increase energy levels, and if we see anyone go over 9, we prepare them to be flashed. Now, step 2, they said was do all the flashes. So all flashes. Hello, Limblum. Welcome in. Perform all flashes. So this will just be in a while loop until to flash is empty. When it's empty, there can no longer possibly be any more flashes. So while to flash So we pop one off, doesn't matter what order they come out in. And this octopus I'll make a little helper method here. So this is 8 directions. So if it's in range, then we yield neighbor I, neighbor j. Oh, and we want to skip that because it doesn't count. All right, that is get neighbors method. So what exactly happens? Each of the neighbors increases by 1. Okay. For neighbor I, neighbor j in get neighbors I, j. Grid neighbor j plus equal 1. And then we do this again. If grid is greater than 9 and neighbor I, neighbor j not in is flashed, so we'll never do it twice. One cell location will only ever be flashed once. Then we put it in there, we add it to the queue. Oh, that should be that. That's it. And after that's done, we have to, all the octopuses that flashed have to reset to 0. So we've got them all here. For I, j in is flashed. Grid I, j equals 0. That's one step. All right, there could be errors here. We could just try running it on grid for 100 times. That grid. Let's just see what the grid looks like. Lots of 6s. Lots of 0s. Okay, interesting. Um, the do it like this. So like this is sort of like a group. And we've got this big group down here. And this is what it originally looked like. Interesting. So it kind of stabilizes. Like what happens if you run it 1,000 times? It's all 8s. That's what I thought might happen. It stabilizes to 8, and then now it's in a cycle. And you could sort of see why that happens, because if one octopus is ahead of another, then basically that octopus is helping the others catch up. Because when it flashes, it's giving energy to all its neighbors. And if they're in sync with each other, then they're just giving energy to each other. Sort of. Well, no, not... Maybe there's some mathematical argument for why it would always stabilize. Anyway, what are we supposed to do with this? Given the starting energy levels of the Dumbo octopuses in your cavern, simulate 100 steps. How many total flashes are there after 100 steps? So we just want to... just increase total flashes. $1,585? Correct. Part 2. It seems like the individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. The first time all octopuses flash simultaneously is step 195. If you can calculate the exact moments when the octopuses will all flash simultaneously, you should be able to navigate through the cavern. What is the first step during which all octopuses flash? Well, easy enough, right? We just well, if we want to compute both part 1 and part 2, we just have to roll them both into one method. So let's say right, normally I mean the proper way to do this would be just to do that and then just reset the grid to what it originally started as, and then do part 2. But if we just do like, I don't know, 10,000 and just say okay, we'll make this a method. Step grid returns the number of flashes. Don't do that. No global variables. And then we just do that. We say step flashes equals step grid. I mean, could it happen in the first 100? Let's just check. So total flashes plus equal flashes. So we keep track of that. And if flashes equals width times height, no, that's fine. Just print. They want it one indexed, right? So print. Let me check. What is the first step? Yeah, I think so. So I don't think it happens in the first 100. No, it doesn't. All right. So then, so that's part one. Okay, in that case, we'll just go. Just forever. So we carry on stepping. No. It needs to be we need to import infinite counting. So this should just count from 0 upwards forever. So we're no longer recording total flashes. If flashes equals width of height, print it's going to be iter plus 1 plus 100 because we already moved 100 spaces. Oh, and break out of the loop. All right, let's see what happens now. 382. So they're saying step 382 is where they all flash. Sounds plausible. I mean, the fact that we've found a spot where they all flash means we're pretty much correct, unless we're off by 1 or something. Correct, yeah. All right, that was easy. I mean, the computation time is minimal. I can't see how you could really go wrong unless I guess the biggest trap people might fall into maybe is doing these flashes in a weird recursive way that doesn't properly avoid like flashing octopuses twice. That's probably the biggest mistake people could make. So to solve that, you need to separate the steps, use queues and hash sets to keep track of things, and yeah. Like if I didn't have this hash set, then you can't really do it. Like you actually need the hash set. There's unless you were just to record some variable for each individual octopus, recording true or false, whether it is flashed before. But then you need 100 of those. Like, no point. Yeah, I was thinking a better part 2 would be, don't tell us that they synchronize, but instead just ask us for like the millionth, how many flashes have happened after the millionth step. So first you would have to find the point where they all synchronize and just add up all the flashes that took place until that point. Then you'd have to realize now it's on a cycle. Oh, wait. Hang on. When they're synchronized, they can unsynchronize again. Because you've got octopuses on the corners, and you've got octopuses on the edges, so it doesn't stay synchronized. But that just makes it more interesting. Then you have to work out what the cycle period is. It's not one, it's actually more than one, so it might unsynchronize and then synchronize again. So you got to work out what the period is, work out how many flashes occur during that period, and then how many periods happen until 1,000,000, and then there's going to be a little bit left over, so you have to compute the partial period as well. I mean, we've had problems of that nature before. It's tough. It is actually a difficult problem, but it's a good problem. And because if they don't tell you that it synchronizes at all, you have to be smart about it and realize that they synchronize.